The heat inside a chip isn't just a side effect, it's a battle that silently burns away billions of dollars in wasted energy. Every second, data centers struggle to keep their systems from overheating, but the solution to this modern problem comes from something ancient, something forged over 1 billion years ago: diamond, a heat crisis, hidden in plain sight. Modern data centers are the backbone of everything digital: cloud storage, streaming, online banking, and the latest AI breakthroughs. But they have a serious weakness. A shocking amount of the electricity they consume doesn't power computing at all. It's wasted as heat. In 2020 alone, data centers in the United States used around 70 billion kilowatt hours of electricity, according to the United States Department of Energy. That's more power than some countries use in an entire year. Much of that energy didn't go into processing or storage. It was spent keeping servers cool. The problem begins at the transistor level. The dirty secret in chips is that more than half of all energy is wasted as leakage current at the transistor level, said R. Martin Rocheisen, an electrical engineer and entrepreneur at Diamond Foundry. This wasted energy leaks out as heat, forcing cooling systems to work harder and harder. The result? A costly, inefficient cycle that heats up chips, shortens their life, and eats into the bottom line of every major tech company. But there's a material that can break that cycle, and its properties are nothing short of extraordinary. Why diamond is different? When people think of diamonds, they think of beauty and strength. But scientists and engineers see something else entirely: a material with unmatched thermal conductivity. Most people do not realize that diamond has the best heat conduction properties of any material, explained Paul May, a physical chemist at University of Bristol. Diamond conducts heat several times faster than copper, which is widely used in heat sinks today. This isn't magic, it's physics. Each carbon atom in a diamond crystal bonds tightly with 4 neighbors, forming a perfect lattice. That structure moves vibrations through the crystal with incredible efficiency, transferring heat away almost instantly. High-end electronics already use diamond heat spreaders in some advanced systems. Within a few years, even the processor in your home PC or mobile phone will probably be attached to a diamond heat spreader, May added. That's how effective it is. The race to build synthetic diamond layers. This thermal advantage has sparked a new wave of innovation. Diamond Foundry, based in South San Francisco, is working on embedding thin layers of synthetic diamond directly onto the back of silicon wafers. The goal is simple: pull heat away from the chip's hottest points before it can cause damage. But the process behind it is anything but simple. The company uses plasma, a super hot gas rich in carbon, and coaxes carbon atoms to arrange themselves in the perfect diamond structure. This requires tricking the carbon into growing as if it's extending an existing flawless crystal. Without that, the crystal structure would form unevenly, like tiling a floor from both ends and meeting in the middle without alignment. Once the diamond wafer is created, it's polished to near perfection. No defect is allowed to rise or dip more than a single atom across the entire surface. That ultra-smooth layer can then be attached beneath a silicon chip, pulling heat away before it builds up. The diamond layers dissipate chip hotspots entirely, Rocheisen said. They're effectively gone. A new player in thermal engineering, but Diamond Foundry isn't alone. Element 6, a subsidiary of De Beers Group, has been working with synthetic diamond for decades. Traditionally, its materials were used in industrial applications like satellite communication systems and high-frequency radio devices. Now, the company is targeting the booming AI and high-performance computing market. The thermal demands of next-generation AI and high-performance computing devices are driving renewed interest in advanced cooling solutions, said Bruce Bolliger, head of business development at Element 6. Earlier this year, Element 6 introduced something new: a copper-diamond composite. Copper alone is already a good conductor, but diamond is far better. By combining the two, Element 6 created a hybrid that channels heat more effectively than copper, but costs less than pure diamond. Copper-diamond composite provides an optimal thermal management solution, Bolliger explained. This could help chips run faster, last longer, and lower the energy bills of massive data centers. It's a practical step toward making diamond cooling more accessible and more scalable, cracking the temperature barrier. But there's a technical challenge that stands in the way. Diamond is usually grown at temperatures over 1,300 degrees Fahrenheit, Fahrenheit. That's too hot for silicon, the material most chips are built on. This is where Shrabanti Chowdhury and her team at Stanford University come in. They've been experimenting with growing diamond at lower temperatures. Their research focuses on polycrystalline diamond, a structure made of many smaller crystals rather than a single one. It's easier and cheaper to produce, but it has a drawback. Polycrystalline diamond crystals often grow vertically. That's great for moving heat up and down, but not across a chip's surface. Chips are wide and flat, so horizontal heat movement is crucial. Finding the right structure at a lower temperature is a delicate balancing act. The work is partly funded by Defense Advanced Research Projects Agency. Yogendra Joshi, a mechanical engineer at Georgia Institute of Technology and a program manager at DARPA, sees huge potential here. Pairing this low-temperature technology with other heat removal approaches could unlock compute capabilities that aren't currently feasible, he said. Chowdhury's perspective is clear. The problem of heat was already there. But now that the growth really came with AI, it's like a hockey stick. We see this problem growing very big. I have not seen anything that was so important so quickly. A future paved with diamond layers. Imagine a chip that runs cooler, lasts longer, and uses less energy. That's the promise of diamond. Of course, none of this happens overnight. Diamond layers are still expensive to produce, especially the thin, flawless single crystals needed for high-end chips. Mass production at scale remains a major obstacle, but history shows that new materials can move fast once they prove their value. Silicon, once costly, became the foundation of modern electronics. The same could happen with diamond as techniques improve and costs drop. And companies aren't just chasing performance, they're also looking at sustainability. Reducing wasted heat means reducing energy use, and that means lower emissions. In a world facing rising energy demand from AI and cloud computing, that matters more than ever. What comes next? The heat problem isn't going away. In fact, it's growing rapidly. AI models are getting bigger. Data centers are expanding globally. Chips are being pushed to their limits. Without new cooling solutions, this growth will become harder and more expensive to sustain. Diamond stands out not just as a fix, but as a foundation for the next era of computing. If this technology scales the way researchers expect, the next generation of data centers may run faster, cheaper, and cleaner, powered by the world's most extraordinary thermal conductor. What do you think? Will diamond cooling become the new standard for chips? Let us know your thoughts in the comments. Because the future of computing might just be built on the hardest material known to science.